In this video, we are going to use some algebra to identify the discontinuities for this rational function, and we'll identify which ones are removable and which ones are non-removable. So let's take a look at f of x, and we need to figure out where f of x is discontinuous. And what makes it discontinuous is whenever we divide by 0. So imagine if you have 1, you try dividing by 0, it's undefined, it doesn't work. So in order to figure out which x values make it discontinuous, we want to factor f of x first. So I'm going to rewrite the numerator, x plus 2, and I'm going to factor the denominator. So that ends up being x minus 5 times x plus 2. Okay? And that's going to be equal to f of x. So now we know that if we plugged in a positive 5, that would create a 0. And if we plugged in a negative 2, that would create a 0. Now, there's two different types of discontinuities. One is going to be removable discontinuity, which is a whole. So this x plus 2 is the same as this x plus 2 on the bottom. If you wrote those out, they divide out. Well, I mean, if you wrote them out, those would equal 1. Okay, x plus 2 over x plus 2, that's just the same as 1. So they divide out. And then you are left with f of x, which will equal 1 over x minus 5. Because you're left with that 1 in the top, there is 1 in the bottom. Now, the removable discontinuity here is going to be a negative 2. And that's because if you plug in a negative 2 in for this x right here, you would get a 0, right? Negative 2 plus 2 equals 0. However, since you're removing that x plus 2, think of that as your removable discontinuity. And that's going to be removed from the actual curve itself, as you can see right here. See how x is negative 2? That's going to create a hole on the curve where you actually remove that point. So that's going to be your removable discontinuity. However, there's still more. If you plugged in a positive 5 right there, you would get 0 as well. 5 minus 5 equals 0. And that would cause our function to be undefined whenever x equals 5. Now, that would be right here. I'm going to draw in what we call a vertical asymptote, which means it's not a part of the graph at all. It's just a dashed line that we use to show where that curve cannot cross over. So as we increase towards infinity, or as our x values increase, we're going to steer away from that x value of 5, and then we get over it, and then we continue on to the right, but we never cross over where x equals positive 5. And that's going to be our non-removable discontinuity, because it's nothing that we removed from the graph just because it was never a part of the graph. So I'm going to write that as x equals 5. Now, we could also look for the location of the hole, right? We know that it's going to be at x equals negative 2 right here. However, where do you get that? And I'm going to write this a little bit better. It's negative 2 comma negative 1 over 7, so a little bit below 0. But how do you get that negative 1 over 7? Well, my function right here is simplified, right? I've got f of x. So what I'm going to do is write f of, but I'm going to evaluate for negative 2, because that's where our hole was happening at whenever x equals negative 2. So then I'm going to rewrite my function. It's going to be 1 over that x minus 5, but now we know that that x is going to be a negative 2, and then we just simplify from there. So I've got a 1 over, it's negative 2 minus the 5, which will be negative 7. So I've got f of negative 2, f of negative 2. So when x equals negative 2, our y value is going to be a negative 1 over 7, and that's how we get the location of that hole. So that hole is going to happen exactly at negative 2 comma negative 1 over 7. And a lot of times on our graph or graphing calculators, it won't actually show the hole. So you just have to figure that out algebraically and then go ahead and put a little open dot there on that curve.